Hello everyone, myself Pavitra Vyas from Department of Information Science and Engineering, Sri Venkateshwara College of Engineering. Today I'm going to explain about multi-level indexing and B-tree. Multi-level indexing and B-tree. R. Bayer and E. McCreight announced B-trees to the world in 1972. Why B-trees came into existence? The reason is that when index file is too large, it has to be stored on secondary storage. It has mainly two problems. The first is that searching the index using binary search requires multiple access to secondary memory. The second problem is that insertion and deletion must be done to secondary memory and sorting of data is to be done. Indexing with binary search tree. To overcome the second problem, the keys can be represented in binary search tree. If the keys are in sorted list, the middle element is taken as the root and a balanced tree is formed. For example, if the list is DE, FB, HN, KF, PA, SD, WS, if KF is taken as root, a balanced tree is obtained. Here is the representation of the tree. Here KF is the root node and it has two nodes. The left node is FB whereas the right node is SD, and FB has two more nodes, that is DE at the left and HN at the right, and SD has two more nodes, that is PA at left and WS at right. Using tree structure, there is no problem of sorting the file when new records are added. The new key is simply linked to the appropriate leaf node. In a binary search tree, each node will have three information. The first one is the key value, second comes the left link, and third comes the right link. Here, the KF is the key value and it has a left link and as well as a right link. The above tree is represented in memory as follows. Root, which is identified in the fifth index. This number represents the index and the second column indicates the key. Third represents the left child and next represents the right child. 0 is the index number of FB and the left child for this is the second one, that is DE, and the right child is the fourth one, that is HM. PA itself is the itself is a child node. DE is also a child node. Thereby, there does not have any subnodes. SD. The left child for SD is PA and the right child is the sixth one, that is WS. Next comes HN. HN itself is a child node, thereby it does not contain any other further nodes. KF. Left child is FB whereas the right child is the third one, that is SG. WS itself is a child node. Suppose a key XF is added to the tree, the key will be attached to the rightmost subtree, that is as the right child of WF. Record contents for a linked representation of the binary tree will be root, that is KF, which is represented in index 5. As keys are added to the binary search tree, it may become imbalanced. A tree is balanced when the difference in height of the shortest path to the tree and the longest path of the tree is not more than one level. Or, a tree is called a balanced tree when all the leaves of the tree are at the same level. Here is the representation of the table, whereas this is an imbalanced one because XF is added over here. Avial tree. Avial meaning it has been named after the inventors Adelson, Willisky and Landis. Suppose the keys are added in sorted order to a binary tree, the tree grows in one direction only. To handle such imbalances in tree, a new class of trees known as avial trees are developed. Example for avial tree. These are the examples for avial tree. There are two features of avial trees. They are minimum level of searching performance. Next comes maintaining avial trees. When new nodes are added, any of the four possible rotations occur in the tree depending on the growth of the tree. The four possible rotations which are included in avial tree are left, left rotation, right, right rotation. They are nothing but single rotation. Left, right rotation, right, left rotation. They are nothing but the double rotation. For a complete balanced tree, the worst case search to find a key is log 2 of n plus 1. For an avial tree, the worst case search is 1.44 log 2 of n plus 2. So, avial tree search is very near to complete binary search tree. So, avial tree helps in faster searching and also it is always balanced. It thus avoiding the use of indexing. Multi-level indexing. Multi-level index is index of the index file. Since index records form a sorted list of keys, one of the keys in each index record, usually the largest key, is taken as the key of the whole record. This is key K2, K3, and it is an address of F2. This is the address of F3. Last one is Kn, address of Fn. Address of F2. Here it is an main index for these files, and next F3 K3 key K3. This represents the index of K3. K3 is an index of these files. Here Fn is the index of these files. Multi-level indexes help to reduce the number of disk accesses and their overhead space costs are minimal. An index file to another index file is multi-level indexing. These are the main keys: 100 till 1000. Its difference is 100, 100, 100. 100, this is the main key, and this index represents 1 to 100. Total 100 files is being represented by a single index, that is 100. 200 represents the files from 101 to 200, and the 1000 index number represents 901 to the 1000. Thereby this is how the multi-level indexing actually works. B trees, working up from bottom. B trees are multi-level indexes that solve the problem of linear cost of insertion and deletion. Each node of a B tree is an index record. Each of these nodes has the same maximum number of key reference pairs called the order of B tree. Order of a B tree is the maximum number of keys in a node of a tree, or maximum number of descendants from a node. It is usually denoted by a small m. While inserting a new key to a node, if the node is not full, simply insert the key. If the node is full, the node is split into two nodes, each with half of the keys. Formal definition of B-tree properties. Properties of a B-tree of order m are: every page has a maximum of m descendants. Every page except for the root and the leaves has at least m by 2 descendants. The root has at least 2 descendants. All the leaves appear on the same level. If the leaf level forms a complete ordered index of the associated data file. Creation of B tree. If the order of the B tree is m, Each node in a B tree can store maximum of M keys. Initially, the keys are added to the node. When the node is full, that is, when the node is overflow, it is split into two nodes, each containing half of the keys. When the new node is created, the largest key of the new nodes must be inserted into the higher level node, that is the key promotion. Continue the process of insertion, splitting, and key promotion until the elements to be inserted into the B tree is complete. Here is an example. Suppose the list is C, S, D, T, A, M, P, I, B, W, N, G, U, R. These elements should be listed in an order of an alphabetical order. First step, we take one by one node and there are 4 blocks over here. We should fill one by one in an order. First comes C and next S is being added over here. D is been added in the second step and even T is been added. Thereby this is in sorted order. Insertion of A causes the node to split. When A is added over here in the third step, it has been splitted over here. It creates a higher level node containing the largest key from both nodes. Thereby, this itself has been splitted. CD and ST, it has been divided into two. And A is added over here because it is less than D. Thereby, the last block's element is being represented as the higher level node. Next comes the addition of M and P. M and P is being added to this node because it cannot be added over left node as M and P is greater than D. Thereby it is added in the right node. Then next comes the addition of I in the right leaf node. I is being added to the right node. Here the node is completely filled, thereby this itself has been splitted into two halves. MPST. I is added over here because it is less than P and it is greater than D. It is less than, yes, thereby it cannot be added over here, thereby it can be added here as it is less than P. Next, the node is split into two nodes having keys IMP and ST. The key P is promoted to the higher level node. Here the P, it is a new node and it is being added over to the higher level node. After insertion of B, W, N into the leaf nodes, B is added here because it is less than D. W is added to the last node as it is greater than T, and then N is added to the middle node as it is less than P, and then here the higher nodes is being verified and then it has been changed over here in the higher level node. When W is added, as W is the highest key in that node, it is added to the higher level node. In this step, insertion of G in the second leaf node splits the node into two as the number of keys will be greater than 4 and key is added to the root node, thus the root node becomes full. Here G is being added. It cannot be added here as it is completely filled, thereby it is divided into half, and G is added to this as it is less than M, and it cannot be added here as it is less than P. Then G is added here. Next, insertion of U and R causes the rightmost leaf node to split. This adds up another key to the root node and thus causes the splitting of node. Thus the tree grows to another level, a new root node is formed. Now U and R. U and R is being added here. When U and R should be added to the last node, but it is not added here because If it is added here, the node will be completely filled and it cannot hold so many elements. Thereby this itself is splitted into two, that is st and then the w. R is added over in this no in this block as it is less than t, and u is added here as it is less than w. Thereby this is the final binary B tree which has been formed. Thereby the elements are in a sorted list: A, B, next comes the C, D, G, I, M, N, P, R, next comes the S, T, U and W. Thereby this is the final B tree which has been completely sorted. Here I complete with my topic. Thank you. Have a nice day.